Hi, in this video, we are going to talk about tree and graph traversal. A lot of the graph problems or graph algorithms, we will visit many, if not all, of the vertices in the graph. So let's take a look at the graph traversal in a little more details first. And there are basically two types of very commonly used traversal techniques. The first one is called the breadth first search. Now, traversal is also referred to as search because basically we are searching through many or all of the vertices, right? So breadth first search, or BFS for short. The other one is the depth first search, or DFS. For illustration purpose, we will actually do both of these using trees because, well, we are familiar with them, and also tree is a graph. Let's first look at breadth first search. Both of these searches start at the root of the tree. So here it starts at 3, and breadth first search then visit the two nodes that are one level away from the root. So 1 and 7, and then it visits all the nodes that are one level away from those. So it'll visit 0, 2, 5, 8, next, and so on and so forth. So the next level of nodes, it visits are 4, 6, and 9. So effectively, what it's doing is that it starts at the root, visit the nodes closest to the root, and then just fan out from there. And this is the order of all the nodes that BFS visits. So depth first search, on the other hand, does something different. While it also starts at the root, it would go as far as it can before it backtracks. So in this case, it starts at 3, go to 1, but instead of then visiting 7, like in breadth first search, it would keep going down. So it will go down to 0, and this is as far or as deep as it can to go on this branch. Then it will backtrack to 1 and visit on the right side, and finishing now the entire left subtree of 3, then it backtracks to 3 and start going down on the right subtree. And so it goes to 7, 5, 4, and again, that's as deep as it can go. Then it backtracks to 5, go to 6, backtracks to 7, and then finish the last branch of this whole tree before it gets back to 3 and completes the entire traversal. This is the path that the DFS takes. But notice that many of the nodes in the DFS is actually traversed through multiple times. So for example, node 1 here, it is first touched by DFS when we go from 3 to 1. It is also touched when we backtrack from 0 to 1, and it's finally actually touched one more time when we backtrack from 0 to 1 on the way to backtrack to 3. So this raises an interesting question: is when do we actually visit or process the data in the node in a DFS? We have a few choices, and they might sound familiar if you remember them from the days when we study binary search tree. So the first one is called the pre-order DFS. And what it does is that it would visit or process the data in the node when it first traveled to the node. So for 1, that's when we first go from 3 to 1. So following this logic, then obviously the first node that we visit, or the first piece of data we visit, is the one at the root, so a 3, and then 1, 0, and 2, and then backtrack to 7, 5, 6, backtrack again, 8, 9, and then we are done. The second order is what's called the post order, and intuitively it visits the children nodes first. A little more formally, instead of pre-order, which is the order in which the nodes are first visited by DFS. Post order is the order in which the nodes are last visited by DFS. So for node, this node here containing 0 is the first one that's last visited, right? So leaving here. So we visit 0 first, and then we visit 2 because after reaching 2, we're no longer coming back to 2, right? And when we go from 2 to 1, 1, this would be the last time we visit 1. So we visit that 1. When we go to 3, we know 3, we will come back to 3 a lot later, right? So we'll then traverse down to a child of 3, and we go all the way to the bottom first to visit 4 and 6 first, 5, and then not 7 yet, but 9, and then now we can visit 8, 7, and finally when all the children of 3 has been visited, now we can visit 3. So this is the post order DFS. Last order, which you are very familiar with, is the in order DFS, and that is to visit the left child first, then the parent, and finally the right child. So visiting the current node is in between the two children. Now, there's a note here that says in order traversal is specific to binary tree, right? Because if a node has more than 2 children, let's say 3 children, then it's not obvious that if we should visit the parent between the first 2 children or the second and third child. And it is called in order DFS because in a binary search tree, which this one is, it literally gives the data in ascending order. Next, let's talk about implementation of BFS and DFS. Now, as a quick review from our binary search tree days, we've already implemented the in-order DFS traversal in the form of a standard iter method, which uses recursion. So what it did was it iterate over the left subtree and then visits or process or yield, in this case, the data in the current node, and then it iterates over the right subtree of the current node. Now, again, this is done recursively, and recursion always has some overhead, and it doesn't scale well, so it doesn't work very well for large trees or graphs. So we want to see if we can do better, and we want to do the same thing, but without recursion. We'll implement pre-order DFS without recursion. So not in order DFS because that's actually a little harder. But if you want to try this yourself first, pause the video now. If you need a little hint, think about the data structure that recursion implicitly uses. Here is a fairly standard way of implementing DFS without using recursion. If you thought about this, the slight difficulty in this implementation has to do with the fact that for every node that we visit, there are 2 more that we have to visit, right? The 2 children. So we really need a way to remember all the nodes that we will visit. So let's start with the list. We'll call this nodes to be processed or to be visited. And the first node that we visit is intuitively the root. And we will keep looping as long as there is at least one node in this list that we have to visit. The first thing we do in the loop is that we will take a node out from the list and visit it, right? And in DFS, well, or in this implementation, we will remove the last node from the list. So we use pop. And the processing or the visiting that we do is really just printing it. So not a whole lot going on here. Just put it on the screen so that we can see what we're doing, right? And then we look at, okay, do we have a left child? And if there is one, we will put it at the end of the list. And then if there's a right child, we will also put it at the end of the list. Now, when you really think about this, we are putting the nodes that we want to visit at the end of the list, and we are removing the nodes that we visit next from the end of the list. So what we're doing effectively is we are using the list as a last in, right? The last put it in the end of the list, last in but first out data structure. And the last in first out data structure is a stack. And when you think even a little more about this, this makes perfect sense because when this is done recursively, recursion is also implicitly using a stack to keep track of all the nodes that it has to visit. Here I already typed the code in my IDE, and we can test it by constructing a binary search tree with the uh, data, and then we just run DFS. So if we run this, here I printed out the tree and then the output of DFS. What you can see here, it first visits 3 and then 7, 8, 9, backtracks to 7 and then 5, 6, 4, and backtracks to 3, then 1, 2, and finally 0. Now, this is probably a little different from what you expected, right? Because we would expect to do the pre-order DFS down the left side of the tree first before going on to the right side. Now, the reason this happened, if you want to think about it a little bit, pause it. Otherwise, if we look back at the way that we wrote our DFS, we put in the left child first and then the right child, right? So when the node is popped from the stack, the right child is popped before the left child, which is why the right side of the tree is printed before the left side. And this is exactly what this slide says. And I'll leave it as a quick and simple exercise for you if you want to fix the code such that it prints out the left side of the tree before the right side. Next, we want to implement BFS, obviously without recursion. If you want to try this yourself first, pause the video. If you want a hint, the code we just wrote for DFS works almost for BFS. You just need a small little change. So here is a standard implementation of BFS. The only change we made from its BFS brethren is when we remove the node from the list, instead of popping it from the back of the list, we actually remove it from the front of the list. Everything else stays the same. So when you think about this, we insert at the end of the list and remove from the front of the list. So the first thing that we put in is going to be the first thing that we take out, which is unlike the DFS, which is the last thing we put in is the first thing that we take out, right? So we are, in the case of BFS, we are using the list effectively as a queue, or first in, first out data structure. So here I've typed out BFS in my IDE, with the only change being pop 0, or removing from the front of the list. And the test code is, yeah, constructing the BST and run the BFS. So if we run it, here's the result, same tree, and the BFS first visits 3, and then 1, 7, 0, 2, 5, 8, and 4, 6, 9, just as you would expect for a breadth first search. The next thing I want you to do, especially if you don't understand thoroughly how DFS or BFS implementation work, or how changing the stack to a queue in the DFS would change the traversal to a BFS, is that you should trace through step by step how each of these implementation work. Draw pictures of either a stack or a queue and keep track of what's being put into the data structure and what's being removed, and convince yourself that yes, indeed, they work the way that they are designed to. In summary, the key takeaway is that in order to do DFS, we use a stack to store all the nodes to be visited, and to do BFS, we use a queue to store all the nodes to be visited. Lastly, we've talked about traversal in the data structure of tree. While tree is a graph, there are differences. So let's talk about the differences between tree traversal versus graph traversal. So first, for a tree, we can always start at a root. But for graph, there are usually not a distinct root node. So a graph traversal can start at any vertex. Secondly, in tree, we usually go from a parent to a child. Now, in graph traversal, while we can go from node 1 to node 2, it's also possible to go from node 2 to node 1, right? So we have to remember to follow the direction of the edges. And lastly, while in a tree, there cannot be cycles, in graph, there can be cycles. So in something like this, right? And when there are cycles, then if we do exactly what we did in tree traversal just now, we would actually traverse or loop forever. So in order to terminate traversal in a graph, we have to, for example, remember the vertex or the vertices that we have visited and not to visit them multiple times. So it is a little more complicated, but by and large, the ideas that we just learned in a tree traversal can apply to graph traversal.